but this will kind of be a good start for that. So with this kind of bracket, right, this quantum numbers bracket, I want to label kind of the axes, and then what we're going to do is we're going to go through and I'm going to introduce and kind of review each quantum number, what the values mean, and talk more about energy level versus sublevel versus orbital, as well as the other quantum numbers, and I'll try to cover some of the questions that I saw in Edpuzzle as well. So what we're going to do first is I'm just going to label the y-axis over here energy. So I'm just going to label this energy with an arrow pointing up. So essentially, the higher up we get in this bracket, the higher the energy. The x-axis isn't really going to have any label because there's no scale or anything for the x-axis. But what I'm going to do is up here at the top, so in the top corner, I'm going to start by talking about each of the quantum numbers, and I'm just going to do a quick summary kind of down the side, and then we will actually fill in this chart. So the first quantum number is the principal quantum number, and that's represented by the letter N. This is the most broad quantum number. This quantum number represents the energy level. Now you're going to hear the word energy level, energy shell. Those mean the same thing. So n equals 1, n equals 2, n equals 3. This is the overall energy level. And so for the energy level, I'm going to try to use different colors just so that we can kind of see everything. For the quantum number n, the values start at 1 and just work their way up. So it's just an integer starting at 1. You cannot have a value of n that is 0. It's 1 up. And with this quantum number, each energy level, so each energy level can hold 2n squared electrons. When you see E minus, that represents electron. So 2n squared electrons. And so what I'm going to do is I'm going to actually come back to the chart itself, and we're going to label each energy level. So I'm going to start all the way down here at the bottom with n equals 1. And so n equals 1. If we think about 2n squared, it's n squared times 2. So when you're doing that, so if n is 1, 1 squared is 1, 1 times 2 is 2. So the n equals 1 energy level can hold 2 electrons. Once we go past 2 electrons, we have to move to the next energy level, and so the next energy level is n equals 2. Right, n equals 3, so I'm just going to write in all of the energy levels here. So the most general energy level, or the most general quantum number, is energy level, n. Now if I come up here and I want to determine the number of electrons, 2 squared is 4. 4 times 2 is what? 8. So n equals 2 can hold a total of 8 electrons. N equals 3, so 3 squared is 9. 9 times 2, 18. So n equals 3 can hold a total of 18 electrons. And then n equals 4. 4 squared, 16. 16 times 2 is 32. So the most general quantum number is n. Represents the energy level. Here's another way of looking at energy levels, and as we get into electron configurations and orbital diagrams, when we look at the periodic table, Let me use my pencil. Row 1 is n equals 1. Row 2, n equals 2. Row 3, n equals 3, and so on. The row, there are some exceptions when we get into the D and the F block looking at configurations, but the row that an atom is in represents the energy level. So sodium is in n equals 3. Okay, so the next quantum number that we're going to look at, so kind of the next step down, is called the angular momentum quantum number. An angular momentum quantum number is represented by the letter L. So I make a cursive L just so that we can tell the difference between an L and a 1, because it is a lowercase l, it's not capital. And the angular momentum quantum number tells us the sublevel that that electron is in. So we're thinking about quantum numbers like an address. All right, so the principal quantum number might be the city. The angular momentum quantum number would be the street. All right, so we're getting more and more specific. So the angular momentum quantum number, represented by the letter L, is the sublevel. Now the values for L are 0 to n minus 1. So your values for L could be anything from 0 to n minus 1. So if n is 1, your only option is 0. If n is 2, your options are 0 or 1, and so on. Now with the sublevel, the reason that the value of L is important is because it tells us the specific sublevel. So if L is 0, the value of L is 0, that electron is in the S sublevel. So now we're getting into something that looks more like configurations, a specific designation. If L is 1, we're in the P sublevel. L is 2, we're in the D, and if L is 3, we're in the F. Those are the only numbers we're ever going to see. Technically, could you have an L equals 4? Yes, you could. You could go into a G sublevel and then H, and then it just goes in alphabetical order, but we don't see that. We're lucky if we see F. So the value of L, the specific sublevel, tells us the designation. And so if we look at this chart again, right, we come down here. N is 1. If N is 1, what are my possible values for L? 0. So here I'm going to put L equals 0. If L equals 0, that tells us we're in the S sublevel. So we can be even more specific, and we will label this sublevel 1S. Now that's our only option for n equals 1. If we move up to n equals 2, we have 2 possible values for L. What are the 2 possible values for L? 0 and 1. L equals 0, L equals 1. Here we start with 0 and work our way up. Now if we know the value of L, we know the designation of that sublevel. We also know the value of N, so we can put them together. So if we're in 2 and L equals 0, that's S. Here's the 2S sublevel. Here's the 2P sublevel. So again, it's looking like with configurations, 1S, 2S, 2P, we keep working our way up. So then, if we go to n equals 3, what are our possible values for L? 0, 1, and 2. So L equals 0, L equals 1. Now be careful, look where the next bracket goes for n equals 3. It comes up here. We'll talk about why once we've labeled all of these sublevels. So now we can label each one of these even more specifically, because we have 3s, we have 3p, and then we have 3d. So notice for every value of n, we're adding another sublevel because there's another value of L. And then finally for 4, right, for n equals 4 up here, we have L equals 0, L equals 1, L equals 2, and L equals 3. So then we can label all of those sublevels. So we have the 4s, 4p, 4d, and 4f. So the value of L tells us the specific sublevel that we are in. So we're getting more specific with where an electron is located. So the third quantum number. The third quantum number is called the magnetic quantum number. And the magnetic quantum number is represented by an M with a lowercase l as a subscript. Right, so we call that M sub L. Now, the magnetic quantum number, we're getting even more specific. This tells us the specific orbital. It gives us the specific orbital designation. So now if we're thinking about an address, the orbital now tells us the house number. Now with the values of M sub L, we have negative L to positive L. So whatever sublevel we are in, our values for M sub L are negative L to positive L. Now, I'm going to go even more specific here. Each orbital, no matter where you are, every single orbital can hold 2 electrons. So no matter where we are, within any orbital can only hold 2 electrons. So we're going to take a look now at this chart, and we're going to look at orbitals. So if we are in the 1s, if L is 0, what is my value for M sub L? 0. So that means I can only have 1 orbital right here. So that means that every single time L is 0, M sub L is also 0. So that means that any S sublevel can only have 1 orbital. So up here next to L equals 0, where I wrote S, I'm going to write 1 orbital. So there's only 1 orbital in the S sublevel. When we are in L equals 1, so we're up here in now any P sublevel. When L equals 1, what are the possible values for M sub L? Negative 1, 0, and 1. Right. Negative 1, 0, and 1. I'm going to split this into thirds. So every P sublevel, has those 3 possible values of M sub L. Now here's how I label them. So if we're actually looking at an orbital diagram and we're assigning quantum numbers, and I'll do M sub L for this, I put 0 in the middle and then work out. All right, so M sub L is 0 and then work your way out. Now up here for the 3p and the 4p, I'm just going to do 0, 1, negative 1. 4p, 0, 1, negative 1. So we're getting more specific about the location. And quantum numbers, these quantum numbers are used to describe electrons. So normally we would have this filled with electrons. We're just pointing out specific ones. So then we have the D. Oh, I forgot to label this. We have 3 orbitals for the P. Right, so up here under where we had L, we labeled, S, P, D, and F. I'm just putting the number of orbitals that we should see. So when L equals 2, what are our possible values of M sub L?
-2, 1, 0.
Right, from -2 up to 2. So -2, -1, 0, 1, and 2. That's 5. So let's see, where do I have, so 3D, I'm going to split it into 5. 1, 2, 3, 4, 5. 4D split into 5. 1, 2, 3, 4, 5. And so what I'm going to do is I'm just going to put the 0 in the middle and work your way out on both sides. 0 in the middle, work your way out on both sides. So this is why S only has 1 orbital. It can only fit 2 electrons. P has 3 orbitals. It can fit 6 electrons. D has 5 orbitals. It can fit 10 electrons. And then if you think about F, if L equals 3, we can go from -3 all the way up to 3. 2, 3, 4, 5, 6, 7. 7 orbitals in F. And so where's my middle? 0, 1, 2, 3, -1, -2, -3. Right, so each one of these orbitals, no matter where we are, each orbital can hold just 2 electrons. Now entire sublevels can hold more than 2 for P, D, and F. Now the very last quantum number is called the spin quantum number. Oops. Spin, which is represented by M sub S, which represents the spin. We have 2 options for an electron, up or down. That's all. And so based on the values, it's either plus 1/2 or minus 1/2. This comes more when we're actually looking at orbital diagrams. So when we actually are drawing electrons into orbital diagrams, you have arrows pointing up or down. If the arrow is pointing up, it's plus 1/2. If it's pointing down, it's minus 1/2. That's it. Now, if we practice looking at some quantum numbers, so let's say, for example, I have an orbital diagram and I have 2 electrons here. I have one pointing up, one pointing down. Now, going along with para versus diamagnetic, so there's a question on what's the difference between para and diamagnetic. That's going to be really when you're looking at an orbital diagram. If you have 2 electrons in the same orbital, now I know that this, right, in order to be a proper orbital diagram should look something like this because you need individual before you pair them up. If you have paired electrons in the same orbital, paired electrons is diamagnetic. Di means 2. So you have 2 electrons paired up. If you have unpaired electrons, that's paramagnetic. That's the only thing we have to know about those terms. 2 electrons, if everything is paired up, there's 2 electrons everywhere, that's diamagnetic. Now, if we're looking at quantum numbers here, let's say that I wanted to assign quantum number for this circled arrow. When you assign quantum numbers, you need to put it in the order of N, L, M sub L, m sub s. We have to give all 4 quantum numbers. No 2 electrons can have the same set of 4 quantum numbers. They can have 3, but not 4. So if I'm looking at this electron right here, we're going to start with n. Start with your most general value. Well, if I know that it's in the 2p, this large 2 here, that's my value of n. So n is 2. If it's in the p sublevel, that means that L is 1. M sub L is the specific orbital. So since it's all the way over here on the left, that value is -1. And then M sub S is just the direction that the arrow is pointing. So if it's pointing up, your spin quantum number is +1/2. Now, if I wanted to draw, or I guess write the quantum numbers for this second one, the one I just boxed, what is going to be the only thing different with these quantum numbers? Abby? Right, so it's going to be 2, 1, -1, -1/2. The only difference is the spin, because those electrons share the same orbital. This is why no 2 electrons can have the same set of 4 quantum numbers. Because even if you have 2 electrons in the same orbital, one has to spin up and one has to spin down. Okay, so this was, I know it was a quick review of quantum numbers, but hopefully this helped kind of bring some stuff back with quantum numbers. Essentially, it is just an address for electrons. So if you're given an orbital diagram, can you find the set of 4 quantum numbers? Any questions on the quantum numbers? All right, so if not, I actually don't have, I'm going to give, because you guys are already